Why don't we go? I don't know. It's up to you. What's beneficial to you? Is it to go forward and then come back to these X's
Yeah.
later? Let's do that.
So I can try those.
Yeah, I felt like I knew how to do them. We just couldn't get an answer that they accepted. Okay, if you just look at that graph, on what intervals is the power increasing with engine speed?
It would be...
Oh, good, we get a multiple choice. How nice.
Yeah.
Really? I mean, so they're looking at the power.
Okay. 2,500 to 5,000?
Correct. In other words, from this point here, which is 2,500, to this point right there. So, A. Makes me nervous to click an answer anymore. Let's see, we want to hit continue, right?
Yeah, there's more
Incidentally,
parts.
last night before I logged off, I did save it. I guess I need to do that every time, right?
Yeah.
Okay. On what intervals is the power decreasing with speed?
5,000 to 6,000.
On what interval is torque increasing with speed? Let's see, I guess I have to hit continue, excuse me. Torque is the blue line.
So, from 3,000 to 5,500. Is that one choice?
Yeah, maybe 54. Now see, here's a beautiful question. This tests your knowledge without making you put down a precise number that might be wrong. So the multiple choice is so much better here.
Yeah.
So what do we get? 3,000 to 54 must be A. Nothing else looks close. And it's decreasing everywhere else. So there must only be one interval. And on what intervals is the torque decreasing?
2,500 to looks like 3,200, and then 55 to 6,000.
Okay, so it really must be 2,500 to 3,000, and then 54 to 6.
So D, yeah.
D, yeah. Now see, we could have taken all day to do those four under the old method. All right, number 9, right?
Yep. Yeah.
Okay, the function has a local what at where? Is it a maximum or a minimum, and at what x value is it?
Maximum at, I think it's 7. I can't really see it.
Yeah. Of 1 In other words, its maximum value is 1 on the y-scale at x equals 7. Okay. Do you understand this point with functions? In other words, if I have a function whose graph looks something like this, and I want local extrema on that function, I'm talking about this point here is a local maximum, and this point here is a local minimum.
Okay.
Those two things share something in common. What is it?
That they exist? I don't know.
The slope of the tangent line is 0 on both of them. If I were to draw a tangent line, it would be flat at some point there. And it's flat at that local maximum or this local minimum. So if we're looking for relative extrema, which is what this is, the way we find it is that we look at the first derivative and find out that it's 0. In other words, the first derivative curve is the graph of all of these slopes. So at this point right there, the first derivative better be 0. Also there. Well, if we look at our first derivative curve, we've got a 0 at x equal 1 and another one at x equal 5. So how to tell whether one is a maximum or is it a minimum? Well, notice here that it's positive after that, which means it's
got to be the minimum.
Exactly. That's got to be the minimum because it increases from the minimum. So x is a minimum, and at 5 it decreases, so that has to be a local maximum. Now, there's what's called the first derivative test, and the first derivative test says that if it goes from negative to positive on the 0, then that's a minimum. If it goes from positive to negative, that's a maximum. All right, so, whoops, clicked the wrong thing. So we could do A. Since it appears to have both, then it looks like A to me. You agree? As a relative minimum at x equal 1 and a relative maximum at x equal 5.
It's so much easier than how many places do we round, or
Isn't that
do we
silly?
put it as a fraction?
That is just so silly, it's unbelievable. I cannot believe how much time we wasted dealing with those problems.
This is probably going to be one too.
It's probably my fault, just because I wasn't that careful doing my arithmetic. All right.
At least these are whole numbers.
Yes, exactly. Find the values of any relative extrema. Okay, so what's the first step?
I actually do not know. Do solve?
Take the first derivative.
Oh, okay.
What's the first derivative? Term for term.
It would be -1.
Negative
Negative
3x
negative
squared
Yeah, negative
In
3x
other words, I
squared.
take the 3, multiply it by the 1. Okay, what's the next term?
Negative 6x plus 9.
Okay. So that's the first derivative, and we know that all relative extrema are going to occur when this is equal to 0. So I'm going to set that equal to 0 and solve this. And what's the best way to solve this?
If I pull out a 3.
Okay, how about we divide both sides of the equation by 3? By negative 3, excuse me. So now we have 0 equals x squared plus 6x plus, excuse me, minus 3. Excuse me. And now that factors to what?
X plus 2x, or x, yeah, x plus 3, x minus 1.
X minus 1, okay? So that tells us where our zeros are. Okay. Now, there's another way to tell whether something is a local minimum or maximum. Although we can certainly apply the first rule that we learned, which is if it goes from negative to positive about that 0, then it's a minimum. If it goes from positive to negative, it's a maximum. Have you learned the second derivative test?
No.
Okay. Well, let's deal with just the first one then. So how am I going to tell? I know that my local extreme are at minus 3 and 1, but how am I going to tell whether it's a minimum or a maximum?
Well, essentially, wouldn't negative 3 have to be the minimum and 1 the maximum?
Remember that you're looking at the x scales here.
Oh.
Not the y.
Wouldn't that be the same still?
Pardon? We don't know. We don't know. Without further analysis, we don't know. In other words, we could be looking at a graph whose maybe something like this, or it could be something like this.
Hello?
Sean, you still there?
Yeah.
Oh, sorry. Okay. I wasn't sure if I lost your audio or not. In other words, we don't know what kind of parabola it is, because if it's the first case, then this is the maximum and this is the minimum. If it's the second case, in other words, if that derivative is like that, then this is the minimum and this is the maximum. Notice this one goes from negative to positive. Well, think about this for just a moment. If we go back to the original parabola that represents our first derivative, we know that that is downward shaping. In other words, that has to look like that, which makes this the minimum at minus 3, and that's the maximum at 1. As opposed to a parabola that looked like this, in which case this would be the maximum and that would be the minimum. So
if the original problem is negative, wouldn't it have to be, like I said, -3 minimum, 1 maximum?
yes. We forgot to do one thing. Sorry. Let's analyze the endpoints.
Or you could just try 1 and see if that's it.
All right. That does seem to make more sense. No. Okay, let's go back. Let's plot this on Wolfram alpha. Okay, so there's our function. And you'll notice that at -3, the slope is 0, and that at 1, the slope is 0. So -3 represents a relative minimum. What did we do wrong with that answer? The function has a relative minimum at -3. Simplify your answer. Type an ordered pair. Nah, we didn't read the directions. -3, comma.
-29.
Looks like 30 to me, but... Oh, did you figure it out? Did you plug it in?
No, I didn't.
Well, to make sure we get it right, let's see. If we got minus a -27 minus 3 times 9 plus 9 times -3 minus 4. What is this value? 27 minus 27 minus 27 minus 4. That looks like minus 31. So -3, -31 is our relative minimum. Are you kidding me? All right.
Parentheses.
I didn't put the parentheses in, and it's not going to let me do it again, huh? It's going to make me do another one?
Yeah. But if it'll go faster if you just kind of plug in like A, use like the letter A, and do all of the checks, and then you can just do a similar question.
Okay, I'm not quite sure I understood what you... So what should I do next?
So in the box, just type in anything.
Right here?
Yeah, in the answer box.
Okay,
Like
and it doesn't matter whether it's correct or not, because we can check real quick. We can see what this maximum is. It looks like we know it's 1. We just don't know the y value. But so when it's 1, we have -1 minus 3. That's -7 plus 9. That's +2 minus 4 should be -2. So this should be 1 comma -2. Might have done my math wrong. When I plugged in 1 minus 1 minus 3, that's minus 4, excuse me, plus 9, that's 5, minus 4 is 1. So that point is 1, 1. How did I get negative anyway? All right, now what?
Similar exercise.
Similar exercise, yeah, because we know how to do this now. All right. So the derivative is minus 3x squared plus 6x plus 24. We're going to divide everything by minus 3. So we have x squared minus 2x minus 8 equals 0. So that's x minus 4 times x plus 2. So our zeros are at 4 and negative 2. Again, we know that it is an upside down parabola, so the point on the left is going to be the minimum. So negative 2 is the minimum. And what is its y value? If I plug in negative 2, I get minus 3 times 4. Whoops, I can't plug it into here. I got to plug it into the original equation. Minus x cubed plus 3x squared plus 24x plus 4. So we have minus negative 2 cubed plus 3 times negative 2 squared plus 24 times negative 2 plus 4. Minus 2 cubed is minus 8, so that makes plus 8. Plus 12 minus 48 plus 4 equals minus 24. So our point is at minus 2 comma minus 24. That's our minimum.
Okay.
Well, the maximum is going to be at 4. So let's go in here and plug in 4 to see what the y value is when x is 4. This is minus 64 plus 48 plus 96 plus 4. That's 148 minus 64, 84. So 4 comma 84 is a maximum. All right, now we can go to 12.
Yep.
Let's write f of x up here. Let's write f prime of x right here. What's f prime of x? You're going to need to use the power rule and the chain rule together. So let's apply the power rule first to the outside. This goes to 0. In other words, when you take the derivative of any constant, it goes to 0.
Yeah.
What's the derivative of that? The chain rule is, well, the chain rule is the derivative, the way you want to think about it is the derivative of the outside times the derivative of the inside. Well, when I take the derivative of the outside, I take the exponent, multiply what's inside, subtract 1 from the exponent, and now multiply the whole thing by the derivative of the inside, which is 3. So, f prime of x, these 3's cancel, and I've got a 2 in my numerator, and I've got 4 plus 3x to the 1/3 in my denominator. So that's f prime of x. Where is a relative extrema going to be?
In the denominator?
Well, it's wherever f prime of x is 0 or undefined. Well, where is f prime of x 0?
Be
nowhere. Only way this thing can be 0 is if its numerator is 0. And since there's no variable in the numerator, there's no value of x that makes f prime 0. Okay? But there's still other points, other values of x that give us great difficulty. What is one of them?
0.
It's whatever makes the denominator 0. What is going to make the denominator 0?
I don't know. Would it be -3?
Negative 4/3. In other words, negative 4/3 will give me 4 minus 4. That's 0, whether I take the cube root of it or not. So this is a critical point, x equal minus 4/3. Now, as to whether it's a minimum or not, let's graph it. Okay, this is a graph of the original function, and the blue is the where on this function is it undefined? Visually.
Across?
Visually. No, this orange is the imaginary solution. Wolfram alpha gives you the imaginary and the real. So the only one we're really interested in is this blue line. Notice what happens. Notice what happens right there. That has a vertical slope. That's where the division by 0 is going to take place. So that is our critical point. But notice that it's not a minimum. Is there a relative minimum in the blue graph?
No.
No, there isn't. And in fact, the minimum is negative infinity. If you carry it all the way out, you can get negative infinity. I guess. Let's see. Is the domain...
Well, I think one of the choices is there isn't.
Right. Now, I was just looking at the domain of the function to see whether x could be positive or negative, and it can be. In other words, I was checking to make sure that this point right here was not our relative minimum. Because if that's where the curve began, then that's where a relative minimum would be. But in this case here, the function has no relative minimum. Three plus quantity 4 plus 3x raised to the 2/3 power. You see a minimum on there? I sure can't see a minimum on there. What do they want? The definition of a relative minimum is that it must have points to the left and to the right that are greater than it is. And there is no point on this graph where I can go left and right and find values greater than where I'm at. That's a critical point, but it's not a minimum. I think this even gives us the derivative. Okay, so here's the derivative, which we got. And gave us the minimum, the global minimum. How is that a global minimum? If I look at the curve, how is there a minimum? This point right here is x equal minus 4/3, but what would the y value? I guess we could plug that in and see. Okay, if I plug in minus 4/3 for x, I get 3 plus 0. So f of x would be 3. Let's try that answer. I don't like it, but so it would be minus 4/3, comma, 0, or 3 rather, is the y value. Well, somebody's going to have to explain to me how that's a minimum. Maybe maybe that's a minimum because it's the first point after like a vertical asymptote. In other words, the slope isn't defined there. So I guess that is a local minimum. Wow, that's a new one on me. I've never seen that situation where they've called that a local minimum. Interesting. Okay, and the relative maximum.
That would be coming up to the asymptote.
Wouldn't it have to be the same thing?
Yeah, negative 4/3, 3.
Based on their logic,
maybe there is no maximum, just a minimum.
Okay, I don't get that either, because if that's a minimum based on their logic, then that there has to be a minimum, a maximum.
Yeah.
It has to be a local maximum. All right. Let's go on. Now let's start by graphing it. Quantity x minus 1, quantity raised to the 2, and I think I may need more parentheses here. Quantity x minus 1 raised to the 2, all divided by parentheses x minus 5. Should be some sort of a hyperbolic curve. Okay. So that's what our curve looks like. We can see that there's a local maximum right there, and there's a local minimum up here. Right?
Yeah.
Okay. I guess we have to do this the hard way. I'm trying to think if there's an easier way to find this value other than differentiating it. I don't think so. Notice that when we look at Wolfram alpha, we're looking for wherever the first derivative is 0. Well, the first derivative is 0 right there, because the slope of the tangent line is 0, and it's 0 down here. So those are the 2 points we're looking for. It's just that finding them is not obvious. Yeah, we're going to have to take the derivative. So g of x equals x minus 1 squared over x minus 5. You take the derivative of this?
Yeah.
Using the quotient rule? You've had the quotient rule, I presume?
No.
Okay. Well,
Maybe.
Quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And simplify. Now let's see. Get rid of that. We could factor out. You almost always can factor out something. X minus 1.
You can get rid of the x minus 5.
Not really, because this is only in the left term up here. It's not all the way across, so I can't cancel it immediately. However,
From the bottom, though, can't you?
no, it would have to be over here in this term. Notice this term is being subtracted.
Oh.
Okay, so let's see, minus an x minus 1. As all I did was factor out an x minus 1 from the top. And let's see, now if we simplify 2x minus 10 minus x plus 1 all times x minus 1. And the right becomes 2x minus x is x, minus 10 plus 1 is minus 9, and in the bottom we've got x minus 5 squared. And that's equal to g prime of x. There's our derivative curve. So where are our critical points going to be? Remember, critical points are where the first derivative is equal to 0 or where the first derivative is undefined.
So 5.
So that's one of them.
And 1 and 9.
Right, that's where the numerator is equal to 0. So what do they want? The first thing they want is a relative minimum. Well, if we look at this graph, we can tell that comes at 1, right? In other words, our three key points are 1, 5, and 9. Well, what happens at 1 is right there. What happens at 5, it's undefined, and what happens at 9 is the local minimum. So here's the local minimum. I might have stated it wrong. This is a local minimum here. This is the local maximum. So the local minimum occurs at x equal 9. And what is g of x when x is equal to 9? Well, we have 8 squared divided by 4. Are you kidding me? Oh, that's 16. Okay. No, it isn't. Yes, it is. Okay. So 9 comma 16 is this point right here. That is a local minimum or a relative minimum. For a relative maximum, that occurs at 1. And what is this when we plug in 1? What's g of x? No, it does. The numerator is 0. So g of x is equal to 0. We don't have a maximum or minimum at 5. That's where vertical asymptote is. But we definitely have a local maximum at 1 comma 0. Find the x values of all points where the function defined as follows has any relative extrema. Find the values of any relative extrema. Okay. In this case, f of x equals 5x plus natural log of x. What is f prime of x?
5 plus natural log.
Now, what's the derivative of natural log of x?
Oh, it'd be e.
1 over x. The derivative of natural log of x is 1 over x. That's just something you got to memorize. Because, well, it just is. Notice that if I take the antiderivative, in other words, if I integrate this, I can't add 1 and divide by the new exponent. I'll be dividing by 0. So I can't apply the power rule to this. And the reason is that the integral of 1 over x is natural log x, just like the derivative of natural log is 1 over x. Okay? So where is this equal to 0? F prime of
0.
x equals 0. No, if I plug in x of 0, I get it blows up on me. It goes to infinity. In other words, 1 divided by 0 is basically infinity. So what does 1 over x have to be to make f prime of x equal to 0?
I don't know.
Okay, I've got 0 equal 5 plus 1 over x. So I got 1 over x equals negative 5. So x is equal to negative 1/5. Notice that when I put in negative 1/5 for x, I get 5 minus 5. So there's one place where the derivative is equal to 0.
Okay.
Let's graph this. Five x plus natural log x. Okay. I get it now. When they graph this like this, every part of the graph that has both an imaginary and a blue part is the imaginary part. In other words, there's only one real answer. Since x can't be 0, because you can't take the log of 0 or negative numbers, so our domain is restricted to x greater than 0 only, which is this part of the graph right there. Even though this blue part over there, that represents the real part of the imaginary solution. You know, if you represent an imaginary number as a plus bi, well, this blue part is the a. The orange part is the b of the bi. So when we're looking at it, we only need to look at positive x's here. So there's no relative minimum on this curve. The minimum is negative infinity. This actually goes all the way to negative infinity, because as you take the natural log of numbers between 0 and 1, like if I take the natural log of 0.001, it's a big negative number. So I can make this as negative as I want, meaning there is no relative minimum.
Okay.
So it's definitely not A. Let's look at maximums. If I look at that same chart, there's no relative maximum. That thing just keeps getting bigger and bigger and bigger. So there's no relative maximum. It's not A or B. There is a relative minimum at this and a relative maximum at that. I don't think so. I say there are no relative extrema. Do you understand that? I'm getting to a point where I'm going through these a little fast.
That's fine.
Okay. Having this curve actually helps, I think. These curves.
Yeah.
Okay? So we have a profit function. Let's plot this, as long as we know we're going to do that at some point. So we're going to take the natural log of minus x raised to the third plus 6x raised to the second. This function looks familiar. Plus 135x plus 1. Okay, let's see what that looks like. Did I got it right? Let's see, natural log, even though it says log, it means natural log. That tells me that over here. Okay, that looks right. And again, the blue part going right is our curve. The blue part going left combined with the orange part going left is the complex solution. So according to this, we have no relative minimum, we have no relative maximum. But it says, find the number of units that should be sold in order to maximize the total profit. What is my answer?
Is it 1?
It's 10. In other words, because x goes from 0 to 10, then I want to produce 10 units. Actually, I would like to produce a billion units, because the more units I make, the more profit I make. So if they're going to say find the number of units that should be sold in order to maximize the total profit, I maximize this number when I let x equal 10 clearly from this graph. I mean, 10 is over here on the bottom graph, but it's a typical log function. It rises slowly. So the number of units, 10. There we answered 10. It's hard to imagine that the answer isn't 10, because this curve does nothing but go down on any number other than 10. Or does it? In other words, we can't see what it does at 10. 10 is to the right. 10 is out here. Wow. All right, let's see. What's the derivative of this? What's the derivative of natural log of x?
1 over x.
Okay, so the derivative of this, if I take the derivative of the outside, I get p prime of x equals 1 over everything that's in there times the derivative of the inside, which is going to go on top. Well, the derivative of the inside is minus 3x squared plus 12x plus 135. That's the chain rule. When you take the chain rule, you take the derivative of the outside times the derivative of the inside. Okay, so this is our function. Oops, I forgot the plus 1 down here. So we want to maximize this thing when the numerator, in other words, we want to make p prime of x equal to 0. That's where we're going to find local maximums and minimums. Well, for this thing to be equal to 0, is all we have to do is set the numerator equal to 0. Because that's the only way it can be equal to 0, is if the numerator is equal to 0.
So just solve.
Yeah, solve that thing there, and that will tell you, let's let Wolfram Alpha do it. Minus 3x raised to the 2 plus 12x plus 135. So we want the zeros of this function.
X equals 9, x equals negative 5.
Okay. And this one here is the minimum. This one here is the maximum. Right? The reason I know is because local minimums happen when the derivative goes from negative to positive. That's indicative of a local minimum. Well, we can't make negative 5 units anyway. So, but we will produce a maximum profit when we're producing 9 units. So, we need to figure out what's the number of units that should be sold. That's 9. Thousand. It's not going to let me do it, is it? It did.
Yeah.
The maximum profit is approximately what? Well, we need to plug in 9 and figure out what the value of that expression is. Now, make sure you don't make a typical mistake here, which is plugging in 9 into the derivative function. What would I get if I plugged in 9 into the derivative function? I would get 0. That's how we solved for 9, was by it's equal to 0 when x is 9. In other words, when x equals 9 here, this thing is an equation. So we don't want to plug in 9 into the derivative function. We want to plug in 9 into the original function. So we have the natural log of, are you kidding me, minus 9 cubed plus 6 times 81, 9 squared, plus 135 times 9, plus 1. Okay, let me look at my calculator. What's 81 times 9? $729. So we have the natural log of minus 729 plus 486 plus 5, 1, 12 plus 1. I'm going to give my brain a break here and add these on my calculator. Shoot. It's 486 plus 1215 plus 1. That's equal to 1702. Subtract 729, 973. So I want the natural log of 973. You have a calculator that'll give you that?
Yeah, it's 6.88.
6.88. So what is our profit?
$7.
In
It says
thousands.
from your dollar.
But in thousands. In other words, in thousands of dollars. So it should be 6880. Was there a third decimal after the 8? When you looked up the natural log of 973?
Yeah, it's 6.8803848082.
So it should be 6880. That's our profit. When we make 9,000 units, we make a profit of $6,880. Doesn't sound like very much. Do not round until the final answer.
I didn't do any rounding, and I got the same answer.
Yeah, we did that. So 6880, right?
Yep.
Terrific.
Yeah. Oh God.
Yeah, it's always a. I wouldn't be betting my life on any of these. Put it that way.
Yeah.
When I go to check answer, I'm so used to getting the wrong answer when I thought I had it right. Different types of lizards vary according the activity level of a certain type of lizard varies according to the time of day. All right, so all they're asking for is the highest of this function and the lowest of this function.
We'll get another shot. I just want to take a guess. Just because I think it's funny.
Just to speed it up, all right?
Yeah. B. Yeah.
Okay, so we need to take the derivative of this thing and find out where those maximums occur. So what is A prime of t?
That'd be 0.024 t squared.
Right. Minus 0.566.
66 t plus 2.302.
Okay. So we want to find out where this is equal to 0. Let's let Wolfram Alpha help us. That's the same function. 0.024x squared minus 0.566x plus, okay. So those zeros occur here and here. Which one is a maximum? Which one's a minimum?
The minimum is on the right.
Correct. So the two zeros are, so the max is on the left. The minimum, however, we got to be careful here because we have some restrictions regarding hours from noon. According to the time of day that the activity is given where T is the number of hours after 12 noon.
It's A. Because wouldn't it be minus 5, so it's 5:15.
Yep. I agree.
And then
6. That would be 18 hours after noon. Right. Okay. Oh, terrific, an easy one. As long as we read it right.
Yeah, I'm hoping to get at least to 20
Okay.
by an hour and a half.
Okay, we should be able to do that. What's f prime of x?
8x to the third minus 12x squared minus 8x. That's it.
What's f double prime of x?
24x squared minus 24x minus 8.
24.
I didn't realize you just kept going down the line with it. That's pretty easy.
Yeah, it is, actually. And same with third and fourth derivatives. So what's f double prime of 0?
0. So what is that? You plug in 0 for x?
Uh-huh.
Wouldn't it just be negative 8?
Uh-huh. F double prime of 4.
I got 280, but that sounds right.
Did you do it on the calculator?
Yeah.
Okay. 280.
Yeah.
Okay, on to 18.
Wish all of them were just that.
Oh, I know, for sure, but it looks like they might be. This is what they should be. I mean, at least this is how calculus should be taught until you master this part.
Yeah.
Now, when you're taking derivative, it always is better to get rid of the radical sign immediately, because I know how to take the derivative of that. What's f prime of x?
Hold on, I'm just writing that out. So
Start with the derivative of the outside.
So the outside, 1 over x squared plus 81.
Hold on. The easiest way, I think, to do this is take the derivative of the outside. Well, that's this. Do you see how that is the derivative of the outside? Because all I did was apply the power rule and assume that this was u. So it was really u to the 1/2. And that's 1/2 u to the negative 1/2. Now I have to multiply that by the derivative of the inside. What's the derivative of the inside?
9.
No, just 2x.
Oh, duh. Okay.
The chain rule is very easy. The chain rule is the derivative of the outside times the derivative of the inside. Okay? So that is equal, I can cancel this 2 with this 2. And so I have x on the numerator, and I have in the denominator x squared plus 81 to the 1/2. So that's f prime of x. So they want f double prime of x.
So would that be, you have to do the same rule or no?
Now we use the quotient rule. Okay? the quotient rule is, the way I remember is it starts with the bottom and ends with the bottom squared. If you always remember that, you'll remember the quotient rule. Because the top is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so let's apply it. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. Well, that's 1/2. I didn't write enough room here. Gosh, I hate that. Let me carry it down here. Minus the top times the derivative of the bottom. Well, we just figured out that the derivative of the bottom is 1/2 x squared plus 81 to the negative 1/2 times 2x. And again, the 2's cancel. So here's what we've got. We've got x squared plus 81 to the 1/2 minus x times x squared plus 81 to the negative 1/2 times another x, that makes that x squared, all over the bottom squared. Well, the bottom squared is pretty easy. That's just x squared plus 81. Because when I square this to the 1/2, just removes the radical sign. So this is f double prime of x.
What, so the bottom, the denominator is what?
Well, we've got some simplifying to do here. The denominator is the bottom squared.
Like
Notice
the wording.
It's x squared plus 81.
No, like, not specific to this problem.
It's the quotient. The quotient
Yeah, just the rule.
The quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that over the bottom squared.
Okay.
Now, there's always some very sophisticated algebra involved when you're looking at second derivatives. We want to simplify this. Now, it's not obvious, but I can factor out an x squared plus 81 to the negative 1/2 in the numerator. Okay, watch what I do here. X squared plus 81 to the minus 1/2. What does that leave behind? Well, when I take this and divide it into that, I get x squared plus 81 to the 1th. And then over here, I've got minus x squared. In other words, that's what's left over when I divide x squared plus 81 to the negative 1/2 into this. Okay, and I still have an x squared plus 81 in the bottom. Now, notice that this x squared cancels with that x squared, and I can simplify that because I have one of those in the bottom. So I'm going to subtract exponents. So my final answer is going to be 81 divided by x squared plus 81 to the 3/2 power. By the time I get done simplifying everything, that's what my answer is. Let's go with that. So I guess I want to type it 81 divided by parentheses x squared plus 81 all raised to the 3/2 power.
Ooh.
Do you want to go through that algebra, what I did? Because it's probably algebra you
No,
haven't done before.
Yeah, I just took a deep breath just before you hit check answer, though.
All right. Yeah, no, I don't blame you. I did too, kind of. Although now it becomes easy. Now that we know what the second derivative function is, we can figure out what f double prime of 0 is.
So it's 81 to the 3/2.
What is 81 to the 3/2?
You do the square root and then
9
81.
cubed. So it's 9 cubed.
It's
Yeah, you
81.
do the square root first, and then you cube it. So what I really have here is I have 9 squared in the numerator, and I have 9 cubed in the denominator, which is 1/9. And you can bet I'm putting it in as a fraction.
How come it isn't just 1? Because if you did 80, like the denominator, 81 to the 3/2, wouldn't that just be 9? Or
No,
81?
it
So
would
it'd
be 9.
81 over
It
81.
would be 9 cubed. So it would be 81 over 9 cubed, which is 727. And then that's equal to 1/9. I just did it a slightly easier way. By changing everything to base 9, I made the numerator 9 squared, and I made the denominator 9 squared to the 3/2, which is 9 cubed. And then doing
my
this
math was off.
simplifies to 1/9.
Okay.
And f double prime of 3. Well, all right. It's not undefined. It's not going to cause division by 0, so it's going to be a number. It's 81 divided by 9 plus 81 to the 3/2 power. Oops, yeah, 3 squared is 9. Type an integer or a decimal. Do not round and then round to 2 places. So what is 81 divided by 90 to the 3/2?
0.09.
What'd you get?
0.09. I just did it in my calculator because it was...
Let's go for it. Okay, 19.
Right.
We're off and rolling. Find the open intervals where the function is concave up or concave down. Find any inflection points. Okay. A function is concave up if its second derivative is positive. It's concave down if its second derivative is negative. We can look at this function and we can see that it's concave down from negative infinity to this point right there, and that's the inflection point. And it's called an inflection point because that's the point that separates where it goes from concave down to concave up. And the inflection point is where the second derivative is equal to 0. So if this is our function, our second derivative function, that's going to be on the 0 line. And that point is 2 comma minus 88 thirds. So we can say that the function is concave down from negative infinity to 2.
Okay.
It's concave up from 2 to positive infinity. So it's concave up on this interval, 2 comma infinity, and it's concave down negative infinity to 2. The function has an inflection point at type an ordered pair. 2 comma minus 88 divided by 3.
Oh, these like last 6. This is how easy it should be.
This is what a regular calculus review looks like. It truly is, as opposed to the garbage we've been dealing with up until now. Okay, let's see. This is the first derivative graph. Now, one of the tricks of calculus is starting with the first derivative and working your way back to the function. So the first thing is asking about an inflection point. Notice that if this is the first derivative, remember that we want the second derivative to be equal to 0 as an inflection point. How many points on this first derivative graph is the second derivative going to be equal to 0? Right there, the slope has got to be 0. Right there and right here. All three of those points, the second derivative is going to be 0. And I know that because I can see that that's a local minimum, that's a local maximum, this is a local minimum. Every time you encounter a local minimum or maximum, you have a flat slope or a derivative of 0.
Is it just going to be the minimum and maximums? Those are the inflection points?
Well, let's take the derivative of this to get the second derivative. What is the second derivative?
So it's 1/3 or 4/3 x cubed minus 3x squared minus 6x.
Okay, so there's the second derivative function. So we want all values of this where this is equal to 0. Well, one thing I can do is factor out an x. What I'm left behind is quadratic. Well, so clearly when x is 0, we have one inflection point. And then the two solutions for this. Let me put that function into Wolfram alpha so that it can give me the two zeros. Because it doesn't look nice. Wow. Those are my two zeros. So there's 3 zeros to the derivative of this function. There's a 0 at 0, there's a 0 at this point, and there's a 0 at this point. Now, when we're examining concavity, we want the well, let's see. Let's just put in all, let's go piece by piece here. Wow, except round to 1 decimal place as needed. All right, let's figure out what these 3 points are. Can you give me a number for this rounded to 1 decimal point?
Yeah. Okay, so the first one, negative 1 point to the first decimal.
Yeah, rounded.
So it's negative 1.27617. So negative 1.3.
And what's the second value? 3/8 times 3 plus that? Should be
3.5.
Yeah. Okay, so here's our zeros. Minus 1.3, 0, and 3.5. Minus 1.3, comma 0, comma 3.5. That it?
There's 2 more parts to this question.
Oh, continue. Excuse me. The function is concave up on what interval? Well, it's concave up when the second derivative is positive. Right? That's the rule. Mm-hmm. When the second derivative is positive, it's concave up. So, this is going to be, let's plot this whole thing here. 4/3 x cubed minus 3x squared minus 6x. In other words, this is the true second derivative before I factor the x out. Does that match? 4/3 x cubed minus 3x squared minus 6x. So we're looking on what intervals that thing is positive. Well, I can see a little interval there, and then from there up. Let's see if it gives us those 3 zeros. Yes. Wow, hold on. The roots, right here. Okay.
Decimal form.
Well, let's figure out, what's the question? Where it's concave up. Okay, so it's concave up wherever it's positive, so it's from minus 1.3 to 0 and greater than 3.5. 3.5 to infinity. Type your answer in interval notation. All right. So, what did I say? Minus 1.3 comma 0. That's one interval. Now I need commas, right? Instead of U's.
Mm-hmm.
And then it's also concave up from 3.5 to infinity. I know, you're amazed, me too. Okay, select the correct choice.
If you saw me in the webcam, I went like this.
Oh, I bet. Yeah, I don't have your webcam, but okay, so select the correct choice here. The function is concave down whenever the second derivative, this function, is negative. So it would be negative infinity to minus 1.3 and 0 to 3.5. That's where this is negative. Negative infinity, comma, negative 1.3, comma, what was the rest of it? 0 to 3.5.
Yeah.
Whoops, that doesn't look like a 0. Okay. You good?
Yeah. I just finished up the last 10 on Friday by myself.
Okay.
But yeah, that works.
Okay, sounds good. This was more fun tonight than the previous.
Yeah.
Gosh.
I don't know if fun's the right adjective.
Well,
Easier, maybe.
For me, man, that was frustrating. To keep putting in answers that I felt were right and it keeps saying no and doesn't do anything more for you. That is hard to deal with when, you don't know that it wants 12/7 instead of this decimal.
Yeah.
But, okay, so let me hit save here. And we go from there. Now, let's see. Before I let you go, let me make sure I've got your desires for other appointments here. Okay. I don't have you down. Yeah, I've got you down regularly on Tuesday night at 6, but nowhere else regularly.
Thursday at 6 too.
Okay. I actually have somebody who took a 7 o'clock slot next Thursday night.
Oh, okay.
You want to, and that's online. So I could do 5 to 6:30, or I could do 5:30 to 7 Thursday.
Yeah, we'll do the 5 to 6:30. That's fine.
Okay, let me put you in here. And then if you want these two spots regularly, I can lock them up for you. Online 5 to 6:30. Do you want to do that, or are you sure enough about the Thursday slot at this point? You can always change it, but this will keep anybody from going. See, people can go onto my website and schedule appointments, so I don't have any choice if they do that. But I have this is a recurring appointment. Let me make that recurring if it isn't. Every week. And then I'll make this one a recurring appointment also. And if you ever need to change it, just let me know. We can do it differently. But at least this will save.
Okay.
Didn't like me doing this all at once. That's all right. I'll figure it out. You're down for next Thursday from 5 to 6:30, and then I'll put you down the week after also. I see what's happening. Okay. All right, Sean.
All right, thank you.
You're good to go. I'll talk to you next Tuesday.
All right, have a good one. Have a good 4th.
You too. Bye-bye.